Welcome, everyone, and thank you for joining the latest advancements in HPCC observability session. Today, we have the pleasure to have Mark Kelly with us. As many of you know, he's a senior architect on the HPCC development project. He has been actively contributing to HPCC platform stability and query performance for over a decade. We'll hear from him later as he walks us through several sample observability reports. I'm Rodrigo Pastrana. I'm a software architect for the HPCC platform as well, and I have been actively contributing to the project for well over a decade now. And in that time, I've mostly focused on third-party technology, connectivity, and interactivity. Today, we'll kick off the presentation with background information on observability. Most of us likely already know and understand the high-level concept of observability, but it's important to set the context for everybody involved. We'll quickly identify the three main components and discuss their purpose, and we'll illustrate how observability helps modern distributed systems operate at optimal capacity and how tracing works at a high level. Then we'll move on to review HPCC's main observability feature. The goal there is to expose the available features, but also how to enable them, and most importantly, how to exploit them. We're going to focus on the recent advancements on tracing of HPCC transactions. And then finally, Mark will demonstrate the power of HPCC transaction fees. Okay, so observability, as it pertains to modern distributed software systems, describes the ability to fully understand the health, performance, and overall behavior of a system. The goal is for the system to provide detailed telemetry information for clear, expedited, and ideally automated problem identification and mitigation. Observability is said to be comprised of three main pillars, which are logs, metrics, and traces. There are different types of data type, and each representing a different aspect of the system. Even though these data types have been existed for a long time, they have been typically been non-standard, disjointed, or obscure. But observability guidelines help unify and expose them in standard formats, which greatly amplifies our ability to analyze our systems, especially when we use observability tools that help aggregate, collate, and link this data in order to visualize a query through a centralized interface. Okay, so now we know observability distinguishes three main data types, but at first glance, they might seem somewhat similar, so let's clearly define them. Logs report and describe events that occur on a system. For instance, an HTTP request has been received, or a connection attempt has failed, or a connection pool has been exhausted. Log information is typically timestamped and includes human-readable descriptions of the event, intended to aid in performance and troubleshooting investigations. An important aspect to know about these events is that they're not necessarily tied to a particular transaction. And on their own, logs lack contextual information and can be far more impactful when coupled with the other pillars. Metrics, on the other hand, report state information about a certain aspect of the system. They provide a quantified snapshot in time of the system to assess how healthy a certain aspect of the system is operating. There's typically two types of metrics. System metrics, such as CPU usage, memory utilization, I/O, or network traffic. And there's application metrics, such as Roxy query response time, or the average count of ESP requests processed per minute in the last hour. If we track and monitor these values, we can infer when a system is going to be overtaxed, or which queries are operating optimally, or which process seems to be leaking resources. Traces are a representation of an end-to-end journey of a transaction through a system. They capture the sequence of operations and interactions between different services and components. This information is critical in expediting troubleshooting, but it also helps us understand how the various parts of the system interact, and it helps us monitor overall performance. These data types are usually generated independently of each other and interpreted in isolation, but their impact grows when they're linked together. Tracing of transactions is especially powerful in complex and distributed systems, which is fairly standard these days. Let's take this sample system where a transaction can be initiated by a client, then received by a front-end server, which makes a database lookup to authenticate and authorize the request. Then that request is handled by a remote service, which in turn farms out the job to multiple backend servers. And finally, the front-end server stores transaction results in a separate data store before responding to the client. In these situations, if we don't have the ability to track transactions from start to finish, it can be difficult to identify and troubleshoot problems, or even know which parts of the system were involved in the processing of the transaction. Even if each component keeps detailed logs of the transaction as it passes through, it usually requires a high level of effort to gather the relevant component logs and associate the related log entries from wherever they were stored. Aggregating logs in centralized systems can help, but a mechanism that links all transaction-specific log information is still needed for efficient analysis. Tracing tackles this challenge by first issuing a system-wide unique ID to each transaction, which is referred to as the trace ID. A unique ID is also issued for each of the major steps in the transaction as it traverses through the system. These are called the span IDs. So these values are attached to the request and propagated along each hop in the transaction as a header called the trace context. As independent components receive the trace context, they're expected to create a new span associated with the incoming trace ID and the parent span. And they also aggregate important information to the new spans, such as a description of the task being processed, target connection information, any errors or warnings encountered, and so on. As the sub-tasks are completed, end time is captured, and the span information is exported individually and independently to a centralized trace aggregator, which gathers, collates, and stores this information and provides visualization tools for analysis and tracking of the trace information. Okay, now let's take a closer look at the components of a typical trace visualization offered by these tools. Traces are typically depicted as waterfall diagrams, which contain a single trace composed of one or more spans. The trace represents a transaction, and the spans represent subtasks within the transaction. The initial span is treated as the root span and reflects the overall transaction start time and total duration. Each span contains a set of known attributes such as the trace ID, the span ID, and the parent ID, which help establish relationships amongst the spans. Some spans have parent-child relationships, and some are siblings of each other. Also very important is the timing information. But different types of spans are expected to report certain basic information. For example, a client span representing a network request will include connection-specific data, such as the target URL and port, HTTP method, and response code. Since each span may come from independent systems or components, the source of the span is also included. Custom information specific to each subtask represented by a span can also be included. This could be anything from a work unit ID to an internal flag used to process the transaction a certain way. Anything that can help paint a picture of what happened during the time in which the operation was executed. The waterfall diagram allows tools to depict timing relationships across the horizontal and ancestry along the vertical. The spans might be colorized to easily distinguish the source component of each span. Any reported error or warnings might be highlighted as well. All of this gives us the ability to easily deduce a lot of information about a transaction, which would otherwise require a great deal of effort to compile. Okay, now we move on to open telemetry, which in some circles, the term seems to be used synonymously with tracing. Open telemetry, or OTel for short, is in fact the de facto standard for observability, not just tracing. Open telemetry does not provide a plug-and-play observability solution, but rather it is a set of very well-defined and documented standards, protocols, methodologies, SDKs in many languages, and tools, which make it possible for independent systems and components to create and share observability information. Due to its popularity, OpenTelemetry has spawned multiple third-party observability ecosystems, which provide powerful and easy-to-use observability solutions. Okay, considering the complexity of a typical HPCC systems deployment, it is imperative to provide high levels of observability to ensure overall health and proper and timely maintenance. So we're committed to empowering our users with all the necessary information and tools to enable deep and clear observability. I'm going to mention our main features supporting each of the three main pillars of observability, and then I'll provide more detail in the upcoming slides. HPCC observability starts with JDA, which has grown to be a very mature log reporting framework utilized by all HPCC components to generate log events. More recently, as part of our journey to the cloud, we recognized the need to ship those logs to remote services such as Elasticsearch or Azure Log Analytics for storage and processing. So we developed the log access framework to abstract away the idiosyncrasies of those backend log storage services and provide a standard interface to query and access HPCC logs regardless of where they're stored. For some users, standing up or setting up a service to collect and process their HPCC logs can be a bit daunting. So we've provided managed Elastic Stack and Loki Grafana solutions, which allows users to set up a log processing service with minimal effort. ECL Watch provides user-friendly log viewers with filtering capabilities which fetch logs from any of the supported backend processing services. Zap reports automatically collect and package relevant information for problematic work units we want to investigate. More recently, we've expanded the Zap report log filtering capabilities, which allow the users to hone in on the most impactful log information. We also offer a work unit postmortem feature, which automatically collects and persists logs related to a crashed work unit. This feature allows us to capture valuable debug information when it's most needed and avoids constant streaming of unused log data, which can result in major cost savings. Application metric support is actually not a new feature either. Several HPCC components have been reporting metrics for quite a while, but they were typically non-standard or buried within the logs or only available through an obscure interface nobody knew about. These drawbacks made it difficult for our users to monitor HPCC health based on internally generated statistics. The metrics manager was developed to overcome these obstacles. It exposes well-known metrics, metric types, and supports popular observability formats such as Prometheus, and is simple to enable and configure. We offer a managed Prometheus solution which deploys a lightweight Prometheus service and configures HPCC to expose Prometheus-bound metrics. Separate from the metrics manager, ECL Watch has recently enhanced its work units metric view, which allows ECL developers to analyze their query behavior and performance. JTrace is our most recent advancement in observability and likely the most impactful feature once it's used in conjunction with the logs and metrics. JTrace is a set of high-level constructs based on OpenTelemetry APIs and standards, which make instrumentation of the HPCC code simple and natural for our developers. JTrace supports the most popular OpenTelemetry trace exporters such as OTLP and gRPC. And we're providing a managed OpenTelemetry collector, and we'll provide a managed Elastic Stack service for trace aggregation and visualization. Okay, so HPCC has been generating robust and reliable component logs for troubleshooting and performance tuning for a long time using the JLog framework. Historically, these logs have been very useful because they contain vast amounts of information. But there is a threshold where too much logging can become counterproductive. And in cloud deployments, they can become unexpectedly costly. It's very important to understand that the amount and types of logs generated can and should be controlled. For a long time, our users were able to let JLog spew out as much information as possible at all times in order to ensure the critical information was retained in a log file somewhere. This was okay because the cost to store huge log files on a local hard drive was fixed, and we accepted the troubleshooting process of waiting until something went wrong to notify a developer or admin, who would then manually log onto multiple machines and manually scour over many text files looking for some obscure hint about an error. So there's three main issues with this antiquated approach. First, issues should be prevented rather than reacting after they have occurred. Two, manually sifting over vast amounts of log data can be very time consuming, expensive, and error-prone. And lastly, we're likely to incur expensive charges for log ingestion if they're processed and stored by cloud provider services. Fortunately, fortunately, JLog is very flexible and its output can be fine-tuned to meet the needs of the business. We can control how much data is reported for each log line. Sometimes the thread ID or the target audience isn't important, and if that's the case, it can be suppressed by a simple configuration change. If we're only interested in errors and warnings and don't care about progress information or detailed debug information, JLog can be instructed to report errors and warnings only. This can help us control the amount of log data generated and stored, which can help curtail costs. Of course, this approach should be reserved for very stable deployments because it discards critical information needed for debugging. JLog can be configured to output logs in table or XML or JSON format. If the logs are intended to be consumed by a log processing service, JSON and XML formats are advantageous, whereas table format has less overhead and is more human readable. To help us prevent issues before they occur, we encourage the use of log processing services such as Azure Log Analytics, Elastic, Loki, and others. Log processing tools allow us to automatically alert when a specific warning or a known log message is encountered, which could force the operations team to act before the warning or event turns into a full-blown error or disaster. Even if we can't prevent the issues before they happen, these log tools allow us to quickly filter and query for relevant log data without the need to gather distributed logs to then manually scour over them, hoping to find relevant log messages. HPCC Log Access allows us to forward HPCC logs to these third-party log processors and continue to attach relevant logs to our ZAP reports, work unit helpers, and ECL watch log groups. Log access is an abstraction layer which allows HPCC to issue log queries to various log processors without forcing users to learn any new log query languages. To make the process of forwarding HPCC logs to a processing service easier, we've provided a mechanism to easily deploy lightweight versions of either Elastic Stack or Loki Stack. This is great for testing out the right solution and the best JLog output setup for our logging needs. Our work unit postmortem feature gathers all available logs related to a given work unit, but does not release the info until they're actually needed due to a work unit crash. The information is packaged and persisted locally, which prevents us from generating costly logs for successful work units and avoids the need to query related logs, which is great for troubleshooting. As mentioned before, Metrics provide troubleshooters contextual information about the system in order to understand what was going on in a system when a particular issue occurred. Considering the heavy use of distributed and cloud-based systems, it is increasingly more difficult to understand the state of the system without explicit metric reports. Our metrics manager provides insights on the state of various HPCC components and can be used to monitor the health of the component, measured performance, and help troubleshoot. The metrics manager supports all common metric types, handles all metric processing logic, and supports reporting to multiple metric services via a plugin framework. It supports reporting metrics either by a push model, where a set of metrics are periodically shipped out to a remote service, or via a pull mechanism, where we expose a service from which the metrics can be requested on demand. Out of the box, we support Prometheus, which is one of the most popular metric services, and Elastic Stack indirectly through an agent which translates Prometheus-style metrics to Elastic. HPCC developers have defined many helpful metrics to report, but users are also encouraged to request metric values they would like to monitor as well. We provide more details on the metrics manager in the resources slide at the end of the presentation. Now on to tracing, the focus of our presentation. Earlier, we learned about the critical aspect of tracing a transaction from start to finish and all steps along the way. And we learned about OpenTelemetry, which provides tools and standards for tracing. HPCC has recently created JTrace, which is a collection of high-level constructs facilitating manual instrumentation of the HPCC platform. It is based on OpenTelemetry libraries and adheres to and enforces OTel standards. JTrace handles parallelism and object life cycles automatically, which makes our developers' task very simple. In essence, all they have to do is strategically decide which units of work should be traced. JTrace ensures tracing context is propagated across internal components and out to and from any third-party system, which also supports OTel tracing standards, which is critical to ensure all related spans are associated within a single trace and their span ancestry is maintained. Similarly to JLog and the metrics manager, JTrace provides many configuration options, such as how much information to include in each span, how to process the spans, and where and how to export the span data. But perhaps even more than the other two observability types, the JTrace output is most useful when visualized by an observability tool. If such a tool is not available, JTrace can be configured to report trace information to our logs, but we insist this feature is used with the tools such as Elastic Stack and ideally alongside logs and metrics. We've also added a column to our logs to include the associated trace and span identifiers so that we can trivially link related logs to spans, allowing us to quickly drill in and identify the root cause of a problem. JTrace supports many standard OpenTelemetry exporters and will soon provide a managed OTel collector, which allows us to target many observability tools, giving our users the options to use the best tools for their needs. Instrumentation of the main HPCC components based on JTrace has already progressed through several iterations, but it's an iterative process which will continue to grow in depth and breadth in order to provide full execution path coverage and maximum troubleshooting impact. Okay, before I turn it over to Mark, I want to emphasize a few takeaways. First of all, as software systems grow in complexity, it is critical to harness observability data. Observability helps us perform real-time monitoring, allowing teams to detect and address issues before they impact users. Troubleshooting can be expedited by detailed context created by the combination of logs, metrics, and traces. Analysis of observability data helps us identify performance bottlenecks and inefficiencies, which can help improve performance. We discussed the main HPCC observability features, which provide vast amounts of the three observability data types. But it's important to understand these features are not automatic, and on their own, they're only data. It's up to all of us, the users, the admins, and developers, to make that data work for us. So here are a few things we can do. Our components are jam-packed with data, but too much data can be counterproductive and expensive. It's important to fine-tune log output, level, and format type to match our needs. In containerized mode, log data is generally ephemeral, and it's best practice to route logs to a log processor and define appropriate retention policy. HPCC's log access feature should be configured to access those logs in order to automatically attach relevant logs to work units and Zap reports. If we choose to use powerful log tools such as Azure Log Analytics, we should set up automated alerts that send emails or texts to the right person whenever a particular error or warning is detected. For metrics to be useful, we need to enable them and route them to an observability tool, ideally the same one as the logs. Most observability services offer visualization and dashboarding tools, which let us graph metrics and apply aggregate functions, which allow us to monitor performance, resource utilization, and provides context for troubleshooting when analyzed in conjunction with logs. If available, alerts and resource auto-scaling rules should be created based off of these metrics. Much like the others, tracing should be configured to target an observability tool, ideally the same as the logs and metrics. On their own, trace visualization helps us find bottlenecks, better understand service and component dependencies, and track transaction timing. But most importantly, it streamlines the troubleshooting process by helping us quickly identify the subcomponent responsible for a failure and quickly pinpoint most causes. And with that, I can now turn it over to Mark for an in-depth analysis of several example trace visualizations. Mark, take it away.
Hi, everyone. Let's look deeper into some OpenTelemetry HPCC traces. But first, I want to mention setup. We must configure HPCC to send OpenTelemetry trace information to a collector, which really just means adding a few lines to the HPCC environment.xml or values.yaml config file. We make sure a collector is running, and then we can submit queries or jobs like we have always done before. So this is a trace of a Roxy query that makes some address cleaning calls through a plugin library and also makes a SOAP call to run another Roxy query. Although this is a simple query, it should prove useful to demonstrate some of the features of OpenTelemetry we are using inside of HPCC. We view this trace from the observability section of the Kibana webpage associated with the collector we used. At first glance, we see time is on the x-axis, and the different parts that make up the query are shown as separate bars on the y-axis. The top bar shows the overall elapsed time of the query. This query was submitted as an ECL job, so the top component shows as a WS work units bar. This span is from the ESP service we submitted the job to. But the run work unit bar just below is a span from the Roxy service. So right away, we can see this trace contains spans from different services on different hosts. This is a key benefit of OpenTelemetry tracing. Spans from different services are all presented together due to the unique trace ID automatically created when the trace begins. This is not a complex query, so there is only one graph present, and the graph1 bar matches the run work unit bar length and overall time. If we click on this run work unit bar, we can see some transaction details. For instance, we see the query global ID. We see the list of slowest activities and their elapsed times. We see this query spent about 4.9 seconds in SOAP calls. We also see this query made 2,324 address cleaning plugin calls. What might be apparent is the mix of both graphical bars from the previous slide and the detailed numerical values shown in this metadata panel. The graphical bars are great for showing when different parts of the query start and stop, to easily see how long they take and to see when different parts are running in parallel. But also, there are fine details about each part that may be important. Showing 2,000+ tiny graphical bars for each cleaning call might not be very helpful here. In addition, sending the trace information for each of these 2,000+ calls to an open telemetry collector on a remote host or in another subscription might be a significant amount of network traffic to consider. One method we have used to help with balancing what to trace graphically to ensure observability of key events without information overload is to only trace calls that take longer than some interesting threshold. In this case, we have decided to collect span traces for address cleaning calls that take longer than 1 second. This method is often called tail-based sampling. Another way to decide what to record is probability-based, where a subset of traces is collected based on a given sampling rate. Let's go to the overall query view again. We see a span for an address cleaning call that took 1141 milliseconds. This shows up because it is a call that took longer than the 1 second threshold we added to the code for tracing these. Clicking on this address cleaning bar brings up the metadata panel and reveals more information. Here are the details of the slow cleaning call. We see the server and port used, the address information, and the actual time on the server spent cleaning this address. The overall time Roxy sees for this clean of 1141 milliseconds is quite a bit more than the actual time spent on the cleaning server of 344 milliseconds. Both times can be helpful to understand possible performance issues. Such a large difference between overall time and server time could be attributed to network transfer or cleaning server scale-up latency. Let's go to the overall query trace again. We also see this query made a SOAP call, and we can see it ran in parallel with the address cleaning calls. The total SOAP call time is 4,947 milliseconds. A SOAP call is made up of several parts, and until recently, we were not able to capture details about these parts. Using the same methodology as before with the address cleaning plugin spans, we can decide to trace the subcomponents of each SOAP call that take longer than some meaningful threshold. Here we see a DNS lookup of the host name took 701 milliseconds. The initial connect to that host took 905 milliseconds. The secure connect TLS handshake took 211 milliseconds. The SOAP call is a call to a Roxy query called stress text. I want to point out here that this Roxy stress text span is actually from a remote service. It is the query run from the SOAP call, but is presented together with the other spans because they all share the same parent trace ID. This is another example of the power of distributed tracing. We can see it took 2823 milliseconds as a complete query on Roxy, but the parent SOAP call took some additional time to process the response. Knowing the time spent in DNS lookups and connects and TLS handshakes and to process responses can be very helpful to understand performance and to find hidden latency. It's important to highlight that this kind of open telemetry tracing can be enabled by default in production. Alerts can be set up for any component or subcomponent that run longer than expected. Going into the SOAP call query details now, we see the metadata for this query and find what might be interesting. Values such as the number of ACK retries, the number of leaf and node cache hits, the number of disk fetches, and the agent wait time are all helpful stats to understand this query's performance. Let's now take a look at an open telemetry trace of a different application. Here is a trace of DFS client, which is a part of HPCC4J. HPCC4J is a collection of Java-based APIs for interacting with HPCC servers and data. DFS client can efficiently read and write remote HPCC data. We again see the overall time in the span at the top, followed by the individual component spans. The first component is fetch HPCC version, which includes the get span just below. What you might notice is there are some gaps between components. Notice the first gap of approximately 400 milliseconds or so between when the overall span starts and when the fetch HPCC version span starts. What is the program doing here? The answer is we don't exactly know, and we won't know until we add more code to the application to observe this time. But it may be complicated because the time could be spent in many different functions and routines. What I'm trying to point out is that adding span tracing is an iterative work in progress. Notice also the gap between fetch HPCC container mode span and the post span. We still have more work to do adding span collection code to be able to find where this time is being spent. I should also mention here automatic or zero-code instrumentation. Zero-code instrumentation in Java uses an agent jar attached to the application. It dynamically injects bytecode to capture telemetry from many popular libraries and frameworks. It can be used to capture telemetry data at the edges of an app or service, such as inbound requests, outbound HTTP calls, database calls, and so on. Zero-code instrumentation also supports method scope attributes as a way to signal where a span should be created without having to code anything. Users can provide a list of methods to trace as a part of the JVM execution. In this trace, we have the get and post spans automatically collected from the Java libraries and jar files the application uses. After the post span, we see the HPCC remote file reader spans, and notice how they are all running in parallel. This was a small example file, so these transfers did not take long. Okay, so that concludes our talk on HPC Systems observability. Here are some resources for more information. Let us know if you have any questions, and thank you.